So today I really wanted to talk about successor measures and self-supervised reinforcement learning. Um, and so just to give a bit of a roadmap over what we're going to cover for the next hour, I'm just going to briefly just define what is a self-supervised RL setting? Like what kind of assumptions are we making? What is it? Why should we care? Um, From there, we're going to move into the most obvious type of self-supervised RL, which is just goal condition RL. So I'm going to talk about some work that we've done to improve goal condition RL because it's a surprisingly difficult setting to get good results in. Show some use cases for robotics, learning from video, and then from there, we're going to move on because their goal conditioned RL has limitations. So we're going to present a more general self-supervised RL that allows for zero-shot RL. And so we'll also talk about what that means. Again, show some kind of cool use cases of PSM and this type of zero-shot RL. And then I think I won't really have time to get to this, but there was a lot that I wanted to talk about. But I wanted to show that we can actually unify a lot of self-supervised RL methods. So this is not a new area of research, and there have been a lot of different perspectives and interesting methods that have come out over the last several years. And I wanted to show that actually all of these can be unified under this idea of a successor measure. Okay, so we want to study a slightly different paradigm for reinforcement learning. And the standard paradigm, should be a very familiar figure to all of you, right? So we have our environment, we have observations, we are this policy or agent that's taking actions in this environment. And the assumption that we typically make, right, is that the environment is giving us some signal about the task, which is this reward. And this is the only signal that we have about what our task is. And so the question that we want to pose instead is what can we learn from reward-free interaction with an environment or an offline data set? So what can we do if we have some pre-training period before we know what our task is or tasks? Right? Like if we know at the end of the day we'd like to obtain some kind of generalist agent that can perform many tasks, is there something that we can do ahead of time if we already have access to offline data or the online environment to speed up mastering these downstream tasks? And so one simple example of this is goal conditioned RL, right? In goal conditioned RL, the agent is being trained to solve a number of tasks, which are just to reach goals, state goals within the same environment. Typically, this goal is just sampled at the beginning of the episode, so we're assuming that we have access to some data set of transitions or states already, and so we can sample from that set of states. And the reason that I'm calling this a self-supervised RL approach is because this reward isn't something that's given to us by the environment, right? We are defining this reward ourselves, and it's very simple to define. It'll look something like this. We receive a reward of 1 if we reach the goal and 0 otherwise. So this is a very sparse reward signal, but we also get very fast policy inference for goal condition tasks, right? By doing this kind of pre-training, this goal condition pre-training, we now have a goal condition policy, goal condition value function. And for any goal, the idea is that, if I've sampled enough from the space of all possible states at training time, I don't have to train on some new goal. If I get some new goal, the hope is that, it's just interpolation and I will generalize to this new goal and my policy will know exactly what to do in order to reach that goal. Of course, you may be asking yourself, what if my task can't actually be defined by a goal state? And we'll talk about that in a bit. So we'll hold on to that for now. So like I mentioned, goal condition RL is surprisingly difficult, right? It's a multitask problem. You have sparse reward for each of these tasks. And so we wanted to try and figure out what are ways in which we can improve training. How can we make the learning signal more dense in goal condition RL? And so we have this one approach that we call F policy gradients, where we drop this idea of being reward based, right? We drop the idea of using this sparse goal condition reward in order to learn a policy. And instead, we're going to train a goal condition policy by minimizing this objective instead. We're going to minimize the F divergence between the probability, the occupancy over states of our policy parameterized by theta and the target distribution. And so this target distribution of the goal in goal condition RL is very simple. It's just going to be a Dirac distribution with all of its mass centered on that goal state. And the intuition behind this objective is that ideally we want the agent to be at the goal state with high probability. As much time as it can spend at the goal, we want it to spend time at that goal and spend as little time or have as low probability as possible at any other state. And so we want to match these two probability distributions as closely as possible. And so just to provide some intuition as to what different F divergences are doing, they denote a notion of distance between probability distributions. So here we just have an example of these two Gaussian distributions evolving over time. And so P2 here is just stationary, so this is our target distribution, and P1 is slowly changing over time to get closer and closer to P2. And as we do that, we can see how these different divergences, forward KL, reverse KL, Jensen-Shannon, chi-squared, they all give slightly different results, but they all have the same trend, which is that their values, the values that they return are decreasing as P1 gets closer to P2. So the first question that we want to ask ourselves is, does this objective actually produce the optimal policy? And by optimal policy here, we mean, does it produce the same policy as what we would have gotten if we'd used that sparse goal condition reward? And it turns out that the answer is yes. And how do we actually optimize this objective? We can use gradients. So if we compute the derivative of that objective, it turns out that we get something that looks a lot like policy gradient, right? So this term is we're just trying to maximize the log probabilities of our policy multiplied by some score function. Typically in policy gradient, the score function is going to be your reward or value function or Monte Carlo predicted value or returns. But here it looks different, right? So this is instead some set of dense weights. And I want to note that this is not rewards because it depends on our current policy. So this changes depending on what our current policy is, which means that this is a non-stationary reward signal. So let's try to understand what this learning signal is doing. So we just have this simple grid world task where the goal is here on the left-hand center. And so here I'm plotting what this, F prime P theta over PG is, as well as what happens to the occupancy of our policy as it's learning with this signal. So in the beginning, all of so red means high value and blue means low value. So all of the high value, the learning signal is all concentrated at this goal point. But over time, as we explore more and more of the environment, we should see this start to spread out, right? Or actually, sorry, what I should say is maybe I think this chi-squared example shows this better. But before we've actually reached the goal, we don't know where our reward is coming from. And so we actually see that we see high value over the entire state space, which encourages our policy to try to cover as much of the state space as possible. And then as soon as we find the goal, then that learning signal is going to concentrate on that goal, and then our probability mass of our occupancy is also going to concentrate on that goal. And so just as a bit of a non sequitur, I wanted to talk a little bit about maxent RL. So maxent RL is this maximum entropy framework that says, there are possibly infinite policies that actually that fulfill the optimal value function. But if we want to limit ourselves to a single policy, and we want that policy to be robust, to maybe have like nice exploration properties, the objective that we want to maximize is now this, right? We now have this additional term that says we want to maximize our expected return, but we also want to maximize the entropy of our policy. And here, what we're maximizing, the entropy that we're maximizing, is that of the action distribution for a single time step output by our policy, right? So this is clearly maximized when your policy is outputting a uniform distribution over your action space. But does maximizing the entropy of the policy actually ensure maximum exploration? It turns out that our objective actually gives us an entropy term as well, but instead of maximizing the entropy of the action distribution, we're maximizing the entropy of the occupancy distribution, the occupancy over our state space. And so this is maximized when our policy is able to achieve a uniform occupancy over the state space. So you can see how these two things are different. And so if we again look at this simple exploration in a grid world, so here green denotes where our agent is starting and red denotes our goal. So we have to go around this wall in order to find our goal. We show what the behavior of our learning policy with two different F divergences, so forward KL and reverse KL. And then we also compare against that standard maximum entropy framework. And so we find that our method is able to find the goal to spread out over the grid world faster and more efficiently compared to pi maxent and reach the goal faster. And so we then also have some results comparing to other reward shaping methods, right? Because you can kind of think of what we're doing as a type of reward shaping. Again, we're not learning a new reward function, but it's a new dense learning signal. And so we can compare against things like Gale and AIM, which are also using discriminator-based approaches in order to use a denser learning signal for, finding a goal or matching some expert demonstration. And we find that we're able to achieve better performance compared to these methods. Okay. So something I kind of brushed over was that FPG objective is looks a lot like PPO, right? It looks a lot like policy gradient. And therefore, it's an on-policy objective, which means that we can only use it in an online setting. So how can we scale to offline data? It turns out that we can use a slightly different approach. We're still going to stick with the occupancy matching perspective, but we're now going to look at the dual formulation to enable offline learning, and we'll get a slightly different objective that allows us to do a very similar thing, but now extend this method to the offline setting. And so this we call SMORE. So this is score models for offline RL. And we again have this distribution matching objective for goal condition RL, but this now looks slightly more complicated. So this constraint is just constraining the visitation distribution to be valid, right? So this is just called the Bellman flow constraint. It has to be valid according to the constraints of the dynamics of our environment. And here, instead of just trying to minimize the F divergence between our current policy and our expert distribution, we're now trying to minimize the F divergence between two mixtures of distributions. So now we have a mixture of our agent visitation and our offline data visitation. This is our offline data set distribution, or you can think of it as your behavior policy distribution, and a mixture of that our goal visitation and again that offline data visitation. And the reason that we have to compute the F divergence between now mixtures of distributions instead of just agent and goal is to avoid estimating this density ratio, which is ill-defined in the state action space when we have zero expert support. So we're trying to cover the setting where we only have partial coverage. And so if we have partial coverage, then computing this F divergence can be difficult or not give us any learning signal. By mixing in our offline data visitation, we ensure that we always have shared coverage between these two mixture distributions. So it's a bit of a trick. And it turns out that, we have to show that using these mixture distributions does still give us the same optimal policy as the true goal conditioned optimal policy that we're trying to achieve. And it turns out that the answer is yes. So if we look at the dual formulation of this objective, and this is very long, and so I just kind of want to highlight what each of these terms is actually doing. It turns out that we're trying to decrease our score. And the reason that we're calling this score is that it's not a value function, right? Because there's no reward. There's no defined reward. Same with FPG. We're no longer talking about defined reward. We're now just trying to maximize density ratios. And so here, instead of thinking about reward and value functions, we can instead think about this as just a model that's outputting a score of how good some state action is. So this objective is trying to decrease our score at transitions under our current policy we're trying to increase the score at the proposed goal transition distribution. And then this term is again just that smoothness, that Bellman regularization to make sure that the scores that we're outputting are obeying the constraints of the dynamics of the environment. And so this is mixture occupancy matching with a dual objective. And so you can see that it maybe doesn't, this objective doesn't look like a contrastive objective, but it does have this contrastive flavor of pushing up certain values and pushing down other values. And it turns out that this link to contrast to a contrastive objective allows us to use tricks from contrastive objectives to improve the stability of this method, which is actually really nice because it turns out that we can achieve better stability compared to standard bootstrapping approaches to RL. So we compare against several different perspectives to this offline goal condition RL problem. So we have another method here that also takes this sort of dual occupancy matching based approach. But GoFAR uses a discriminator, which means it's going to be less stable compared to our method, which has this more contrastive flavor. We also compare to behavior cloning methods. So this is just standard supervised learning in the goal condition setting, and then also a weighted version using a value function. We also compare with another contrastive RL approach, and then just standard RL with sparse reward. And so we see that SMORE is able to achieve the highest performance across a lot of different simulated robotics tasks and locomotion tasks. And we show that we can actually also do this from image observation. So this does scale to high dimensional tasks. And we have to use a slightly different set of baselines because not all methods work on images. But we again see that we're able to achieve better performance compared to these baselines. And so another question that we can ask is, how well does our method do as we reduce our data coverage, right? And so we had designed this objective to be able to work in partial coverage settings. And so we basically here reduce the amount of expert data that exists in the offline data set and compare against GoFAR. And again, GoFAR is also using this occupancy matching perspective, but they're using a discriminator in order to compute the learning signal. And that discriminator is more susceptible to data coverage. And so we find that GoFAR, so the performance of everything drops as we reduce our data coverage, but we find that SMORE is able to drop more slowly. So it basically behaves more gracefully as we erode this data coverage compared to GoFAR. Okay, so maybe we want to ask ourselves, what can we actually do with goal condition RL, right? So we know that we can do fast policy inference given some new goal condition task, but we'd like to be able to do more with this, right? And so one thing that we can do, it turns out, is that we can use goal condition RL to train from video. So let me just first try and give some motivation for what we want in this setting. So we'd like to be able to achieve a generalist home robot. And this is a very hard problem because there are very diverse environments, like every home is completely different. There are very diverse tasks that we'd like for this robot to be able to perform. And so if we think about what are the components that we need from a solution to solve this problem, we probably need some very good representation that captures the commonalities, the structure across these different diverse environments. And we also need a generalizable reward function that can generalize across these different tasks and across these different environments. And the problem with trying to do standard in-domain RL or imitation learning, any kind of robot learning in this setting, is that collecting this robot data is inherently scarce and very expensive to collect. And so what we would like to do is to be able to learn from human videos as a big offline goal condition RL problem. So there are a lot of human video data sets available, just from computer vision, just from YouTube, from DIY type tutorials. And so here are just some examples of human videos, specifically from an egocentric perspective from the Ego4D dataset, right? And these human videos are rich sources of goal-directed behavior. we can assume that this behavior is near optimal, that it covers the type of diverse tasks that we would like a robot to be able to perform. And so if we think about how we can actually write down an offline goal condition RL objective for this human video data, it would look something like this. So this is just the standard offline goal condition RL objective, which just says I want to maximize my discounted return subject to this constraint that I need to stay close to my data set distribution, right? I don't want to move outside of my data support and have my value function extrapolate wildly. And so this is just a regularization term to make sure we stay within our offline data support. So this is mathematically sound. This is the standard objective used in offline goal condition RL. The problem here is that I have these actions A in this objective. And we don't have actions for this video data, right? This video data you can think of as just state-only trajectories. So unfortunately, we can't optimize this objective directly in practice. But it turns out that if we again look at the dual formulation of this objective, we get something that looks like this. And if we think about what are all of the components that we actually need here, right? So here we just need the probability distribution over goals. Okay, and that's easy for us to get. That's just taking the last frames from all of these different videos. Here we just need the initial frames from all of these videos. And here we just need consecutive frames from these videos, from these trajectories. And nowhere do we actually see actions. Oh, I thought I had another thing here that just says, we don't have actions here. Yay, dual. But I didn't have that. Okay, so this leads us to our method, VIP, towards universal visual reward and representation via value implicit pre-training. So in practice, what we do, so this is kind of like an empirical trick, but instead of learning a value function neural network, instead we're going to embed value in a representation. So we're going to say we're going to learn a representation. So we're just going to train an encoder that takes in video frames and maps them to a point in this representation space. And the way that we train this representation is that we say that L2 distance in this representation space corresponds to that goal condition value between those 2 points. So now this gives us both a reward. We can use this goal condition value function as a reward signal for downstream tasks. And that representation is a nice representation now that we can also use for downstream tasks. Okay. So again, this objective actually has, again, a time contrastive flavor. So let's assume that V star is something that's known for a second. It turns out that we can rewrite this objective into something that looks like an info NCE style objective, right? Where we have these positive pairs of examples of just states within the same trajectory, states that are on the trajectory towards our goal. And then we also have these negative examples, which are just pairs of states that are not that are just pairs of states. And so this is kind of different from a standard positive negative pair in a contrastive objective, because instead of saying that we want to push negatives away and pull positives together, we are still kind of doing that. But here our negatives are just neighboring frames in our videos. And so instead, what this is doing is it's saying, I want my neighboring frames to always be a unit distance apart, is a very specific distance apart. And I want to hold that true while also pushing together maybe initial states and goals. And so this looks similar to a standard temporal contrastive objective, but it is slightly different, right? So a standard temporal contrastive objective is pushing together neighboring states and pushing apart anything that's not neighboring. So that's what TCN, time contrastive networks, is doing. And so we can train VAP and TCN on a very toy data set on just 100 demonstrations and plot those distances over a held out test set. And we do this for Franca Kitchen. And so here we see that our VIP leads to a very nice, smooth path in our learned representation space. Whereas TCN, it does still capture temporal information because it was designed to, but it's not nearly as smooth as VIP is. And so this hopefully gives you a bit of intuitive understanding of what these two objectives are doing, right? Okay, so now we want to show what we can do now that we have this goal condition value function that doesn't have actions and this representation. So we're again just looking at Franca Kitchen. So we have these 12 Franca Kitchen tasks with 3 different viewpoints, 2 different initial states. So easy just means it's closer to the goal, and harder means that it's farther away from the goal. And so these are just some example images of what these tasks look like. So the first thing that we're going to do is just look at trajectory optimization. We're going to use MPPI to optimize a trajectory. So it just means that we're rolling out trajectories and we're going to pick the best one and then take that first action and then do that over and over again. So this requires access to a dynamics model. And we don't want to mess around with learned dynamics models here. We're just trying to evaluate our representation, or just trying to evaluate our value function. And so we're just going to use the simulator as a ground truth dynamics model to roll out these proposed action sequences. And we'll use our value function, so that's what this pre-trained rewards is, to evaluate these rollouts and take the first action of the best sequence and repeat. And so here we're just evaluating the representation's capability as pure visual rewards. We're not learning a policy yet. So if we look at our performance, so here this is really small, but we're just comparing against other representation learning methods like CLIP, MoCo. So this is have more of a contrastive flavor again. This is just a pre-trained ResNet on Ego 4D, and this is a temporal contrastive objective, R3M. And so we're just using these representations, a distance in these representation spaces again as a notion of progress towards our goal. And maybe it's not a surprise that, VIP has been trained for this representation to capture this type of progress, and so we're able to achieve much better performance. So for success rate, we want this to be higher, and for this robot pose error and object pose error, we want these things to be lower. So VIP is able to robustly minimize both robot and object pose errors. And it turns out that if we scale our optimization budget, and so here this just means the breadth, right? We can roll out more trajectories. We can increase the horizon for which we roll out those trajectories. By scaling this optimization budget, we just continue to get better and better performance with VIP, which means that our value function is very consistent at different horizons. Whereas R3M and ResNet do not have this kind of smooth learning signal, and so increasing the budget doesn't actually lead to much better performance. And then here are just some qualitative results showing our method compared to a baseline and the kind of policies that we're able to achieve. Okay, and so I just want to show some real world offline RL results that we use with VIP, right? Standard offline RL is not very data efficient. It's most effective when we're able to label it with this dense reward. And the problem, especially in robot learning, is that people find it harder to implement and tune compared to behavior cloning. And so people would much rather just collect expert demonstrations when possible and tune and train with behavior cloning. And so you could argue that behavior cloning is still the dominant approach for real world robotics. And so the objective that we're going to use to extract our policy is reward weighted regression. So this is a very simple objective. We're just going to weight transitions according to our pre-trained rewards, according to our pre-trained value function on this Ego 4D video data. And so you can think of this as boosting the attention to keyframes if the reward is good. And the nice thing about this objective is it's just a one-line change from BC. We're just adding this weight term from our value function. And our hypothesis is that this is going to outperform behavior cloning even on top of the VIP representation that we're learning. So we have these robot tasks in the real world. And I want to just note that the data sets that we're collecting are very small. So for all of these data sets, we only have 20 demonstrations, except for closed drawer. So here we have 30. We have 10 demonstrations, but also 20 failures. And all of these tasks are difficult in different ways, right? Like one is because we're dealing with an articulated object or transparent object, a soft object, or a deformable object. Okay. And so here we just report some of the results. So we have a VIP with reward-weighted regression versus behavior cloning, and then the same thing on top of that temporal contrastive objective on Ego4D data. So that's what R3M is doing. And one thing that I want to note is that we also show what our results would be if we didn't use Ego4D for pre-training. So this is what our performance would be if we ignore Ego4D and we only train on these 20 demonstrations. And so what we see here is that this pre-training is necessary to perform few-shot offline RL, and VIP is uniquely effective for it. Sorry. And then here again, we just have some videos showing the policies that are learned for closing this drawer, pushing this bottle, and pick, place melon, just picking up and placing this squishy melon onto a plate and folding this towel. Okay. So I mentioned this a bit earlier, but there are some downsides to goal conditioned RL, which is that not all downstream tasks are goal conditioned. So I kind of maybe skimmed over this, but all of the tasks that we were evaluating on across all of those projects were goal conditioned tasks. So we couldn't actually use these value functions that we'd learned, these representations, on tasks that are not goal conditioned. And so that brings us to the question, how do we construct self-supervised objectives with guarantees of generalizing to any downstream task, not just goal conditioned ones? And another way of putting it, if we want to think about this from this dual perspective, from this occupancy matching perspective, is how do we extend these prior works to any state visitation distribution? So one concept that I want to define before we proceed any further is the notion of a successor measure. So we're going to define the measure over future states visited. And that just looks like this, right? So this is just a discounted, you can think of this as the sum over our discounted probability of being in any future state, given that we started in SA. And you can think of this also as the discounted measure of ending up in some particular state, S plus. And so the most common form is going to look like this. So this is, again, just giving us that discounted measure of ending up in state S plus, given we started in SA, and assuming that we were following this policy pi. So the successor measure is dependent on the policy. And then the reason that we care about the successor measure is that it's very easy for us to extract Q functions and policies if we have this successor measure. It turns out that we can just multiply this successor measure by our reward in order to get the Q function. And then once we have the Q function, we can just compute the argmax of the over actions in order to get the optimal policy, right? And so the nice thing about the successor measure, the reason why we want to decouple these two things is because it gives us a reward independent representation compared to Q functions, which are reward dependent. We also now just have this very nice linear objective for policy optimization, where the optimal policy is just an argmax of m times some reward. And so you can now kind of sketch out this framework of how we can use the successor measure, right? So we can now have this reward-free phase where for any state, any action, any future state, and any policy, we want to learn the successor measure. And then we can have a reward-based phase. So after our pre-training procedure is done, we now have a phase where we're now told what is our task. And we're assuming that we're, given this reward, we can assume we were given the reward function itself. We can assume that we just have transitions with reward labels, whatever. But as soon as we get that reward, we can now extract the optimal policy directly. And so that's why we can call this zero-shot RL, is because we don't have to do any additional fine-tuning of the successor measure. We can extract that Q function just directly from the successor measure that we learned in the pre-training phase. Okay, this sounds really nice, but it's intractable, right? That if you look at that reward-free phase, this is a lot of stuff that we have to cover in order to learn these successor measures. There's a lot of different successor measures we have to learn. There's potentially infinite policies that we have to compute the successor measure for. So how do we actually characterize all of these possible policies? And you can kind of think of bringing goal condition RL into this framework But goal condition RL is limiting the space of policies that they consider, right? We're only considering optimal goal reaching policies. And so that brings us to proto-successor measure. The motivation comes from the observation that the Bellman equations are affine. And so that means all valid solutions to the Bellman equation, all valid solutions to learning the visitation distribution for all possible policies lies on a convex hull. And so the boundaries of this hull is defined using this non-negativity constraint, right? Because these are probabilities. So this has to be greater than or equal to 0. But every point in this plane corresponds to a valid visitation distribution according to some policy. And because it's affine, it means that there exists a set of basis vectors that can describe this entire convex hull. And so then, if I have this set of basis vectors, I can compute the visitation distribution for any policy as just a set of weights on those basis vectors. And so I can represent this plane as all possible weights for these basis vectors. So we're now going to derive a method for actually trying to find this a basis set to describe this convex hull. So we're going to take the successor measure. So it turns out that the successor measure I can also write in terms of that Bellman update equation. They follow a similar Bellman equation as state visitation distributions. And from that observation, from that convex hull, I know that I can break down that successor measure into this linear form, right? So here phi are my basis vectors, W is just some set of weights on them and a bias term. So for any given reward function, I just need to solve this linear program on W. I just need to find the right set of weights that maximizes, that leads to the policy that maximizes that reward. And so our loss objective is nothing special, actually. So this is really just the Bellman update or a TD update. This is equivalent to TD error, but I've just plugged in this phi W plus B for that successor measure. And we just have to minimize this for all possible policies. And this allows us to achieve a representation that's not dependent on policy, right? Because this phi does not have policy dependence. And so this is a truly universal representation. And so the benefits of this is that, again, we can just perform this very simple inference on any reward function. We get zero-shot extraction of near optimal policies, which is great for environments where the reward is maybe not known ahead of time, where we have this compute budget or we have this time where we can pre-train in a self-supervised manner to make things more efficient downstream. And so because we have this kind of pre-training and fine-tuning or zero-shot extraction phase, we actually call this a behavioral foundation model, right? And the impetus for this is kind of like from the successes in large language models and computer vision, where they have developed these autoregressive objectives, these self-supervised objectives for learning on all of the sequential data, and then downstream fine-tuning for good performance on downstream tasks. So if we just look at, again, some simple grid world results. So here we just have a grid world environment. So black just represents walls, so barriers. And then here we just have color-coded the value functions being learned by PSM. And so again, PSM was trained not knowing where the goal was. It was just given data for this grid world environment. And then we give the goal at inference time and extract the Q function without any additional training. And we can compare, so there are actually other methods that do similar things that also have this kind of pre-training and zero-shot extraction procedure, but they have a very different parameterization and a very different perspective for how they came to their objective. So this is forward-backward, which does something similar. And we see that you can also use Laplace methods to do this. And we see that here, there's actually a much smaller variation in the value. So for both FB and Laplace methods, we find that the value function generally just gives very high values across all cells, right? Whereas we can see a much bigger contrast with PSM. And maybe you're thinking, okay, well, the contrast, the amount of difference that there is in the value doesn't necessarily matter too much. But the problem is that if your value function is outputting very similar values for different states, that means a small amount of error in your value function can correspond to changing the action that's taken. And we find that to be true in practice, is that PSM is able to achieve a much more accurate optimal policy, whereas FB and Laplace demonstrate mistakes. So on the right-hand side, we just have it's maybe too small to see, but we have the arrows corresponding to the value function that's learned. So PSM is more sharply concentrated on the optimal state action pairs. And so we can scale this up. So that was just a demonstration of what do the value functions that we learn, like what do they look like? But we can scale this up to locomotion tasks, different kinds of tasks, right? So again, here we're just training on this domain. And then at test time, we're giving these different tasks like stand, run backward, jump, walk. And then we're evaluating the performance of all of these different methods. So FDM here just corresponds to a forward dynamics model. So it's learning the one-step forward dynamics predictability. SVD is performing a singular value decomposition of the successor representation. So I'm not going to get into these methods, but they're somewhat similar to what PSM is doing. HILP is just a variation on FB that makes a couple of changes. It reduces the tasks to be goal reaching in the pre-training phase to just make things a little bit simpler. And then they use a more performant offline RL method for extracting those successor measures. So they use IQL to learn the features. And overall, we find that PSM is able to perform consistently better or competitive to these baselines across all of these environments. Okay. So I want to show what's possible with something like PSM. What can you do with this kind of behavioral foundation model? And so one thing that we can do that's just a bit of fun is just incorporating language into this zero-shot RL. So in order to do that, we have this three-stage procedure. And each of these stages, I think, can be implemented in lots of different ways. And so we just kind of picked something that was simple. So we're going to assume, in order to incorporate language into zero-shot RL, and by this I mean that we're not training language condition policies. Instead, we're going to use a fine-tuned VLM. So if I want to use language to describe some task that I want my behavioral foundation model to perform, I'm going to use a fine-tuned VLM to generate video trajectories according to those language commands in my target domain, in the target domain that the VLM was trained on, right? So this is going to be a different domain from the target domain that I'm trying to perform my task in. I then need to have a project step where I map from those generated observations in that video domain, let's say, to real observations in my target domain. So in practice, we can just use like nearest neighbors in some SIGLIP in this some representation space. And then I have an imitate step, right? So now that I have mapped those observations to observations in my target domain, I can just extract a policy to match that demonstration. I can assign reward to the observations in that trajectory and then use that to extract my policy zero shot using something like PSM. And so that gives me a policy that matches the demonstration and therefore a policy that actually obeys that language command that I provided in the very beginning. And so we find that this actually works in practice. And so, I can give very simple language commands like cartwheel or crawl like a worm or bunny hop or jump high. And I can actually extract out policies with no additional training that kind of look like they're obeying these commands. And it turns out that you don't actually even need this imagine step, right? We can actually throw out that VLM, but that means that we can't use language. But here, instead of using language, we're saying you could actually just use a real video or demonstration. And what this is relying on is the power of the representation that you're using to perform this nearest neighbors mapping from this this domain into this target domain. And so it is very dependent on the quality of that representation. And again, in practice, we find that using SIGLIP works pretty well. But then we can get really nice policies that look like this, that are trying to match the yoga poses in these videos that we found on YouTube. Okay, so we've talked about self-supervised RL. What is it, and maybe why do we care? We've talked about goal condition RL, how we can improve upon the standard goal condition RL algorithms and their use cases. We've generalized from goal condition RL to every possible task by using successor measures. We've shown how we can use these behavioral foundation models to generate language condition policies. And now I want to talk about a unification of self-supervised RL methods. And in order to do that, I'm going to have to provide another roadmap. I don't have a really easy way of doing this that isn't going to just show look like I'm showing a list of methods. But again, one of the self-supervised RL methods that we can look at is goal condition RL. We can also look at mutual information skill learning. So this is using mutual information in order to learn diverse skills that cover our state space or state action space. And so this is also a method for learning, the useful policies when we don't have any reward information. Forward backward representations. So I kind of touched on this, but this is kind of similar to PSM, and so I'll talk a little bit more about that. There's also an approach called proto-value functions. And then we can also actually fit world models into this, right? So again, world models, you're just learning dynamics models, one-step transition models, or multi-step from a data set or from an environment, right? And so again, this is an objective that does not assume any access to a reward. Okay, so if we consider the space of goal-reaching policies, the connection between these goal-conditioned value functions and successor measures is quite simple, right? And so here the idea is just that we know that the Q function is proportional to the successor measure subject to that reward. But the nice thing is that our goal condition reward is very standardized, right? So remember, it's just that sparse reward where we receive a 1 when we reach the goal and 0 otherwise. And so that means that this relationship between Q and our Q function and our successor measure is always fixed, no matter what our goal is. And so at policy inference, the reason this looks so much like successor measures is that we're just detecting the goal and extracting the optional policy from this goal conditioned Q function. In missile methods, so this mutual information skill learning, we're trying to maximize the mutual information between states and skills. So these skills are represented by some latent representation space Z. And so there's between a specific state and a skill, or between transitions and skills. And these missile methods typically rely on this lower bound that requires training a variational distribution, so Q of Z given S. And depending on assumptions of the policy coverage of this skill set, so often this skill set is not going to be covering the entire space of possible policies in the same way that we do with PSM. But it turns out that you can actually write down the successor measure for any skill Z using that variational distribution and transition distributions and that prior over Z. And so policy inference can be performed by just searching through this space of skills. But there are some downsides to this because there's no kind of guarantee of full coverage of the space of policies. And successor features are very similar. They're kind of a more specific instantiation of successor measures, because the idea behind successor features is that we are being given a state representation that is linear with respect to all possible rewards that we care about. So this doesn't cover all reward functions. It only covers a specific reward function class. And in successor features, you're learning this cumulative state feature psi, which is just the discounted sum over those state representations into the future. So you can kind of think of it as capturing the future occupancy of states but using this representation. And so again, it turns out that we can actually extract out the successor measure, right? The probability of you being in some future state, given that you started an SA, from these representations. And so it's because this is just a linear model, this is just the closed form solution of that linear problem, right? And then we can also extract the optimal policy or the optimal Z for some reward by performing this argument. And forward-backward representations are just a specific instantiation of successor features where they're also learning the successor measure, but they're breaking it down in a different way from what we do with PSM. So they break it down in this F transpose B. And so F has this dependency on the reward or on the policy. And then B just looks like this. And so policy inference, this specific instantiation that they choose was so that policy inference becomes very simple. You don't even need to perform any kind of optimization. You don't have to solve a linear program. It's just going to be B times R. And assuming that this is B is something that you've learned or that you've parameterized with the neural network. And so then you can just extract it once you have this state. Okay. Proto-value functions, the idea behind this is actually somewhat similar to PSM. The idea is that we're going to decompose our value function into a spectral basis. So they're also decomposing value functions into a set of basis vectors, similar to what we did in PSM. But the span of value functions using basis functions actually represents a smaller class of value functions than the set of value functions that can be represented using the span of the successor measure. So basically what this means is PSM, if we fix the dimensionality of the representations that we learn, of the basis vectors that we're learning, PSM actually has more coverage. It has more representational power compared to the basis functions learned with proto-value functions. And so that's what this theorem says in our PSM paper. And so it just means that PSM is more efficient. The basis set that we learn has more representational power compared to proto-value functions. There's also this slightly different idea about learning controllable representation. So this is the reason this fits in here is that it's still a self-supervised approach. The idea is that we're going to assume an exogenous block MDP, and that just means that we're assuming an MDP where, as part of our state space, there is some exogenous process that is not, and that means it's not controllable by the agent. And so our goal is to try to learn a lossy compression of the state space where we'd like to identify that exogenous component and remove it, right? And that means that we've basically made our MDP smaller. It's easier to solve downstream control problems with a smaller compression of the state space. And it turns out that the way you can do this is to use a classifier to model k-step inverse dynamics. And then you get actually a k-step successor measure of the behavior policy, right? So now we've extracted information about k-steps into the future, which is how we can extract this k-step successor measure. And then we also have some recent work trying to find these controllable representations that instead use this recursive computation to find the inverse dynamics. And so we can also model the successor measure, but only of a random policy. So this is kind of the connection to successor measure for controllable representations. And then finally, world models. So world models encompasses learning single-step dynamics models or latent dynamics models or even generative models that predict several steps into the future. And the connection between world models and successor measure is that you can think of them as a generative form of the successor measure, right? The way that we had defined successor measure is, it outputs some probability of being in some future being in some future state. The way that we have learned something like PSM is that we are mapping this into a representation space. We're learning representations that you can use to compute this value. But you can also train this as a generative model, right? You can have a generative model actually output that future occupancy at either in a latent space or in the state space. And so policy inference here is also looks a little different. It would just look like planning with the model, right? So ideally, you can have this controllable world model that you pass in the reward information, and it would automatically generate for you the successor measure or the path into the future, the trajectory that maximizes your return. And so, we have this nice paper that came out pretty recently showing this unification across these different self-supervised RL perspectives. And it just summarizes the different ways in which you can approximate the successor measure from the things that these different methods actually learn. It shows how policy inference is different for these different methods. So policy inference can be cheaper or more expensive depending on the quantity that you actually learn. And then we also show how we can actually map from any of these ideas to a representation space and what a state equivalence that representation space captures. And then we also kind of have this nice analysis of these different approaches with their pros and cons. Some pros can be they're relatively simple to train or to learn. Or maybe, they constrain the space of reward functions or policies that they consider. Or they could be very expensive if they cover kind of the space of all possible policies. If they're trying to make fewer assumptions, then they're going to be more computationally expensive. Or it could be that policy inference is very slow, depending on the quantity that you're learning at training time. And so we kind of get into what all the pros and cons are of these different approaches. And so the nice thing about this, is that it unifies all of these very different perspectives. A lot of these are very different approaches at self-supervised RL, right? This is a very broad class of methods, right? The only thing that holds them together is that they don't use reward. And so it's really nice to be able to show that they all have this something in common, which is learning the successor measure. And so just to end, I think that self-supervised RL is a very practical and realistic way to train generalist agents. I'd like to see more work being done on trying to develop better approaches for self-supervised RL. And based on this unification, I think that we shouldn't necessarily be spending time thinking about all of these different perspectives and trying to improve methods from those perspectives. And instead, we should just think of everything through the successor measure. And we can focus on developing better approaches to approximate the successor measure. And part of that is maybe should we be using representations? Should we be using generative models? There are definitely trade-offs of both. Based on how we learn the successor measure, what is the best way to perform policy inference, right? And we would like to be able to use assumptions that we have about specific problem domains. So how can we restrict the space of reward functions or policies we consider using specific assumptions, maybe using specific data sources or partial coverage data sets, depending on our domain. Okay, and so with that, I can end. Thanks a lot to my group who has done all of the work that I've been able to talk about today. And then here are just snapshots of the papers that I covered.